Before we go to your lecture, can you share with us some background knowledge about yourself?
I did history and archaeology in the BA, and I went for masters at the beginning into archaeology. At that time, I became what is called in archaeology the architect of excavation. And actually I had something like 15 years of field experience in archaeology, quite a lot. Now, in order to get deeper into this business of field archaeology, I decided to do masters in architecture and city planning. So I started master at actually I did my first degree in the Hebrew University of Jerusalem, and then I went to the Technion for masters. And there was a master in city planning, not so much architecture, but city planning, and somehow I was captured by city planning. And decided, so I did my MA studies at the Technion and went to the London School of Economics and to do a PhD. Now, in the London School of Economics, I met Derek Diamond, that became eventually my tutor, and he said, listen, there is no way. I wanted to combine archaeology and modern town planning, and he said, no way to do it. You do first planning and then do whatever you want. So I did PhD in planning at the London School of Economics. After that, went back to archaeology, but eventually, and I was actually in between the two domains for some years. Eventually, I was carried away, so to say, by urbanism and planning. And that's basically the story. And I think the turning point was Berkeley. I did postdoc in Berkeley. And there I decided to move basically to urbanism.
What was the moment that you could see within urbanism in spatial planning the connection with self-organization?
Yeah, well, self-organization, I got into self-organization as a consequence of a research I did in the early 80s. I did a big study on the Israeli-Palestinian conflict. And I was looking at how to call it, conceptual framework to study the issue. I was not happy with what existed at the time. You know, there was a big division between positivism and social theory-oriented studies, structuralism, humanism, etc. And I met at that time someone by the name of David Bohm. David Bohm is one of the greatest physicists of the 20th century, to my mind. And I was influenced in a way by his writing, and started to get more and more into the domain of complexity. Specifically so after I met Hermann Haken, which was, I think when was it? It was mid-80s. And since then, I got deeper and deeper into the domain of complexity, self-organization, and so on, and have applied it, firstly, to the Israeli-Palestinian conflict. I wrote a book, which actually came out in the Netherlands, in Kluwer. And the title of the book was Implicate Relation, and the subtitle, Society and Space in the Israel-Palestinian Conflict. And this was the first step, serious step, into complexity. This project was finished by the end of the 80s, beginning of 90s, and then I decided to move out of the conflict a little bit into cities and urbanism.
Because at that time, it was at the very early stages of complexity thinking. It was still very much chaos. What was the label?
Yeah.
Complexity started emerging. Were you on your own, shouting your message sort of in the empty desert, or?
At the beginning, yeah. It was basically on my own. I was inspired by a lot of what Herman Haken said. I was captured at that time a lot by the whole study of cognitive mapping, and since then I actually combined the two. So at the beginning it was on my own, but as it happens a lot, suddenly you realize that you are not on your own. Suddenly you realize there is this guy over there, that guy over there, and we gradually met each other, and during the years it became a whole domain of what we now call CTC, complexity theories of cities, with people like Peter Allen, Michael Batty, Denis Poumen, and others, of course. Yeah. I will talk about, I'll try to answer the question, what makes cities complex. As you can see from the top, this talk started a couple of years ago when we had a conference in Delft. I will add to the Delft conference a new notion that we have just recently published. It's called the information adaptation. And you will see a bit as the talk develops how it feeds into this issue. Okay, let's start. And this is the argument. Cities are complex systems. That's the main point. And as such, they are similar to many other complex systems in nature. And as we will see in a minute, most theories about complexity started studying complex systems in nature. But cities are also artifacts, artificial entities, and an artifact is by definition a simple system. So the question is, what makes cities complex? And the answer is very simple, we, the urban agent, each one of us is a complex system. And the fact that we are part of the city, we are part of its dynamic, makes cities complex. Now to elaborate, and in this respect, as it's written here, cities are hybrid complex systems. They are combined of an artifact, which is the buildings, roads, etc., and the human beings, the agents that are active in the city. Now, to elaborate this argument, I will look at similar entities in nature which might remind one about cities. For example, the beautiful structure made by termites or bees, etc. And I will try to elaborate what makes us human. This is a big philosophical issue, as you might know. What makes us humans different from animals, if you wish, if we are different. And I will argue that we are different in the following way. We are different because we have a very specific cognitive set of capabilities. One of them, which is very well known, is of course language. But I will direct attention to another one, which is called chronostasia, or what is called mental time travel, our ability to flow in time back to the past and forward to the future. Following this suggestion comes a question: how to conceptualize an agent that is taking decisions based on this cognitive capability, and the answer comes from a recent study that we have just finished. And this is a study that is based on information theory. And I will try to argue that information theory provides a good starting point to theorize about human behavior in cities. And I will give a few examples, of course. Let us, so this is the plan. Let us start with some introductory notes about complexity theories and about complexity theories of cities. I can start, or we can start the story with an interesting monography by Schrödinger, one of the most famous physicists of the 20th century, who wrote this little book which is called What is Life? And in this book, Schrödinger answered by reference to the notion of entropy. Material objects, he said, are subject to the second law of thermodynamics, which basically is to the process of entropy, which means that the system goes from order to disorder. And there are many theories that says that this is actually what happens in the universe, if you wish. Life, so says Schrödinger, is the exact opposite. Life becomes possible by preventing entropy, by holding it back. How do we do it? We extract what he calls negative entropy from nature, which means we undergo this process of metabolism by which we take energy from the environment. And by using this energy, we actually prevent entropy, or if you wish, prevent death in this respect. Now, at the end of this little book, which has nothing to do with complexity theory directly, there is a little statement that you can see here. Organization is maintained by extracting order from the environment. And in this little statement, Schrödinger actually anticipated what came after 3 decades when Ilya Prigozhin got his Nobel Prize, among other things, because of his idea of dissipative structures. He is one of the founding fathers of the theory of complexity, and in his Nobel talk in 1977, he make a direct link to the notion of entropy, and actually he's repeating what Schrödinger suggested 3 decades earlier, as you can see on the board, and there is also a nice a graphical illustration. What I want to emphasize in this connection, in this place, is the following. Already in this talk, Ilya Prigozhin makes a reference, that just by chance, to cities. And in a few minutes, you will see how. So let me first say, or introduce the basic ideas of complexity theory. I will do it in a very simple way by a very fast survey through the various theories, when each theory actually emphasizes another property of complex systems. Let's start with Ilya Prigozhin, we have just discussed. Ilya Prigozhin came with a theory which is called dissipative structure. I will not go into the details, but I will emphasize one property which actually Prigozhin emphasizes, which is a complex system is an open system. Open in the sense that it is all the time interacting with its environment. It is never closed, okay? It's all the time interact with the environment and all the time in what is called far from equilibrium condition. The system is all the time on the move. It never stops, okay? Even when we see order, it's not equilibrium. It's not equilibrium in the, let's say, economic sense. We never have a state of equilibrium. We are all the time far from equilibrium condition. And in this respect, this is a complex system. So this is one property. A second property comes from the studies of Hermann Haken, with whom we are still have very good research connections, as you will see later. And Hermann Haken emphasized another property, which refers to the way order comes into being. And his basic idea, which is based on the phenomenon of the laser beam, his basic idea is that order comes into being bottom up by means of interaction between the many parts of the system. Out of this interaction, something new emerges. And this is the new order. And all this, and this is important, happens spontaneously, which means by means of self-organization. So a second interesting aspect is that complex systems emerge bottom up out of the interaction between their parts, and they achieve order spontaneously by means of self-organization. And synergetics, which is the name of Haken's theory, goes one step further. It says that once order comes into being, it enslaves the parts. Okay? Just to give you a simple example, take language. You see, each one of us was born into a certain language. And each one of us was enslaved by this language. Before we had time to think about it, we are already enslaved by the language. And once we accept the language, we strengthen the language. So we have here a process of circular causality. The parts create the whole enslaves the parts, and so it goes in what is called circular causality. This is Hermann Haken. A third beautiful theory is Mandelbrot's theory of fractals, which points direction or attention to three interesting phenomena of complex systems. The one is the notion of self-similarity, which means that the part is similar to the whole, or vice versa. And you can go up and down the scale. This is where the notion of scale-free systems comes from. You can go up and down the scale and find, in principle, the very same structure. This is a property of self-similarity. And then there is the property of fractals, fraction. What Mandelbrot taught us, that even though we are educated to think in terms of whole dimension, 0 dimension, 1 dimension, 2 dimension, etc., we can also think about broken dimensions. And this is where the name of the theory comes from. It's a fraction. And the basic idea that we have in between, let's say, 1 dimension and 2 dimension, that is, in between straight line and a 2-dimensional entity, let's say a page, we have a lot in between. We can have structures that might be typified by, let's say, 1.5 dimension, 1.8 dimension, which they are much closer to 2-dimensional, but still not there, and vice versa. Okay, so this is the second property, which is a broken dimension. And the third one is also very, very interesting. It has to do with the notion of iteration. What Mandelbrot theory shows that once we have a very simple algorithm, but this algorithm goes in circles. You remember what Haken said about circular causality. This algorithm goes in circles. We start with very simple relations, but as the circles go on and on, as the iteration go on and on, we get more and more complex structures. So the basic notion here is that what seems to us a very complex system or very complex structure might be an outcome of a very simple process, but a process that goes in iteration. And this is one of the reasons that the whole theory of fractals came hand in hand with the development of computers, because this is the only way to test this idea of, let's say, thousands of iterations, and suddenly, after the 1001, you have a new order emerging. So this is on fractals. Chaos theory, which is very well known, chaos theory and the metaphor, which was invented by Lawrence, who also one of the inventors of the theory. Okay, the butterfly metaphor that says that a butterfly is doing like this in one part of the world, in the other part of the world we have storm. And what is interesting here in terms of properties is the property of nonlinearity. A very minor event in one part of the world in this story, or in one part of the system, a very minor event might cause a very dramatic outcomes, and vice versa too. Okay, a very dramatic effect might cause nothing. And if you want to think on this property in connection with your profession, planning, you can think that a minor act of a single person in a city can be much more influential than a very well-established plan made by professional planners and so on and so forth. So this is the property of nonlinearity. We have to be very careful about thinking about all phenomena in terms of causality, okay? Because this idea is somewhat counterintuitive. Actually, our whole experience is based on causality, okay? So this is another property. The last one, which I will mention here, has to do with networks. Network is the new science of network is the most recent addition, so to say, to the large body of complexity theory. And it suggests that complex systems are essentially networks. And the new science of networks study the structure of the network. And by studying the structure of the network, we can get a lot of insight into the way complex systems work. Okay, so this was how much? 10 minutes introduction to complexity theory. Now, a complexity theories of cities. I promised you to go back to Ilya Prigozhin Nobel lecture, and it comes from there. And there he says during the talk, are most types of organizations around us of this nature that I was just explaining? And the answer is negative. Obviously, in a town, in a living system, we have a quite different type of functional order. To obtain a thermodynamic theory of this type of structure, we have to show that non-equilibrium might be a source of order, and as you have just seen, all theories of complexity see in non-equilibrium a source of order, and in fact, all theories that I have introduced were actually applied to cities. For example, Prigozhin's theory of dissipative structure was applied by his student, Peter Allen, from England. Synergetics was applied by Weidlich, who is co-friend actually of Hermann Haken. We have applied a lot of synergetics to cities, Haken and myself. Michael Batty and Peter Longley wrote a lot about fractal cities, and there is a beautiful book, one of the first in the domain of cities. Cellular automata, which is the methodology, how to study complex systems, were applied to cities, agent-based modeling, and more recently, network theory. And we have lots of books and many, many papers. And as in complexity theory in general, so in complexity theories of cities, each theory emphasizes another property of cities as complex systems, and actually you can guess what each theory emphasizes. Prigozhin's, so to say, dissipative cities. That's the way we refer to cities described by, or analyzed by, or theorized by his theory. Dissipative cities emphasize the interaction with the environment. A city interacts with its environment. Haken, the bottom-up emergence of cities and the principle of slaving, Mandelbrot fractals, etc., etc., etc. But still there is a dilemma. There is a dilemma because cities are, as I said before, are large-scale artificial environments built of smaller-scale entities, like building roads, each of which is built still with smaller artifacts, etc. And an artifact, as I said before, is by definition a simple system. So, what is it that makes cities complex? And the answer is simple. Again, as I said before, the urban agents, we. Each of us is itself a complex system. So, just to illustrate this point, let us have a look at few slides. What you see on top left is a car. The car is essentially a simple system. You put a driver behind the wheel, and it becomes complex. Okay? An empty city, just the buildings, is a simple system. You put inside people, you make it complex. Take a supercomputer. Looks very complicated, which is, but essentially, it is a simple system. Put a person behind this computer, you get a complex system. Actually, there is a beautiful book by Weizmann, and you might know it. And the book is, the title is The World Without Us. And the book was written with no connection at all to complexity theory. It was just a kind of science fiction, if you want. And the basic question of the book is what would happen if for some reason we, all of us, evaporate and the world remains without us. What will happen to this magnificent culture that we have built here in the last millions of years? Okay? And he shows that very quickly our big culture will be, how to say, swallowed by the universe, actually, by the environment, and then by the universe, for the simple reason that we are not here. In order to maintain our cities, we need to repair the city, to take care for it, to fix something that gets wrong, to maintain it. Maintenance, very simple process, is a very important process in keeping a system alive. It might be a human being, a single person, and of course, a whole city. And in a sense, planning is about maintenance. Okay, so let us elaborate a little bit on this argument, and let us look at entities in nature that might look like artifacts, okay? Here are some nice examples, beautiful architecture made by termites, honeycomb, dams made by those little animals. Now, there are two important differences between us and them. And they are written on the board here. All those beautiful structures made by animals are what is called extended phenotypes. Richard Dawkins called them extended phenotypes. I will explain it in a minute. I mean, they are kind of extension of the bodies of the animals who made them. So this is, it's okay. So this is one important difference. And the second one is that we, human beings, we have a very specific memory, which most animals, not all, there is a big argument in the field about it, but we have a very specific kind of memory, or very property, interesting property, which is called chronostasia, or in a simpler way, mental time travel. Okay? We have the ability to travel back and forth in time. Actually, as we will see, planning and design are one of the outcomes, are two of the outcomes of this property, and there are many others. So, and again, on this issue, you see, this is a nest made by a bird or two birds. And what is interesting in this picture is that the nest was made from artificial entity. This is a nest that I found next to our department in Tel Aviv. In the city, all the raw materials, so to say, are artifacts, actually. But the nest itself is part of nature. Or what Scott Turner called extended organism, which is similar to dogs, not identical. And the same with the other beautiful constructions. And the basic idea is that, that those animals who made those beautiful structures, they had no choice but to do it, and to do it in this specific design. Okay? They do it in this design, and this is design in this sense. You see, there is a saying. Is anyone here reads Hebrew? I can tell you whatever I want about this statement. Now, in the Jewish tradition, there is a saying that all is expected, all is predetermined, but still, we human, we have a choice. There is no choice for us but to take a decision. And this is what this statement says. Now, animals have no choice. We human have a choice. Nature does tell us, let's say, make a shelter. But nature would not tell us how to make the shelter. And we have a lot of choice in this respect, as you can see here or here. So the production of artifacts, and this is my argument here, basic argument, is unique to humans. If you look at human beings from very early age, you will see that they exist always with artifacts, all kinds of artifacts. And actually, we humans undergo, unlike animals. Animals are subject to what is called biological evolution, Darwin's biological evolution, etc. We humans are subject to two evolutionary processes. One, like other animals, we are subject to Darwinian or biological evolution, but at the same time, and in parallel, we are subject to cultural evolution. And unlike biological evolution, which is relatively very, very, very slow, that we actually can ignore it when we look at a small portion of time, cultural evolution is very, very fast. And within a person's lifetime, we can see that we all the time have to adapt to cultural changes, to new artifacts, as we saw last night with 2 kids, with 2 machines, and so on and so forth. And this is so with small artifacts and big artifacts, etc. Okay. Let's elaborate a little bit about this property in relation to cities. And let's do it first by reading a little bit from Through the Looking Glass, beautiful book by Lewis Carroll. You might know it. And within this book, there is an interesting discussion between the White Queen and Alice. And I don't understand you, says Alice. It's dreadful, confusing that the effect of living backward, the Queen, and the Queen answer, it always makes one a little giddy at first. Living backwards, Alice repeated in great astonishment. I never heard about such a thing. But there is one great advantage in it, that one's memory works both ways, says the White Queen. And Alice responds immediately, I'm sure mine only works one way. I can't remember things before they happen. And the White Queen replies, it's a poor sort of memory that only works backwards. And in fact, the White Queen is right, because our memory, not only in this imaginary kingdom, but our memory works both ways. It works backward, we remember a lot of what happened, and it works forward as well. And this is called chronesthesia. Nowadays, we know, there is this beautiful film, Back to the Future, where the whole idea is part of imagination, but now we know that there are certain parts in the brain who enable us to think backward, to remember things that happened to us in the past, but also to think forward, to remember or to think about things that have not yet happened to us and might never happen to us. And this is called mental time travel. I mean, this ability, and the same place in the brain does the job in both directions. Okay, so this is what it's now. And this is a very interesting cognitive property that is now subject to a lot of research. What I want to emphasize here, that not only we have this property of mental time travel, but we cannot not travel in time. And you can see it in a very simple way. Any of you who tried meditation know that the first step in meditation is not to think about the past and not to think about the future, but to remain here and now. And this is very difficult mentally. It's not easy to be here and now. It's because our mind is running back and forth. And it's very difficult. And actually, studies show that we spend more than 50% of our time being somewhere, in the past, in the future, not here. So this is what I would like to emphasize. And on this basis, I want to suggest what is written here, that planning and design are direct manifestations of this property of mental time travel. And we cannot not do it. We cannot not plan as human beings, and we cannot not design, actually. So planning and design are natural or basic cognitive properties of human being. So this is the first or the core of both planning and design. And then during the evolution of culture, we have transformed it into a specific profession. But basically, it's part of human nature. We cannot not plan and we cannot not design, and from here follows a very interesting outcome or property again, which we call planning behavior and design behavior. Planning behavior we already introduced a few years ago, and design behavior we introduced in Delft in that conference. And the basic idea is that a lot of our behavior in cities is based on those two properties of, okay, this is just to illustrate this. Urban agents are behaving and acting in response to plans or design. In other words, in response to a reality that doesn't yet exist and might never exist. Okay, so think about us as rational creatures. We are acting actually in line with or according to a kind of invisible cities. And invisible cities reminds one of the most beautiful books by Italo Calvino, the title of which, surprisingly, is Invisible Cities. And, you know, in this book, he goes through a whole series of cities that he describes. And here is another one, which is called Fedora. And in the center of Fedora, he writes, in that metropolis stands a metal building with a crystal globe in every room. Looking into each globe, you see a blue city, a model of a different Fedora. Every inhabitant visiting it chooses the city that corresponds to his desires. And as you know, the whole book is a kind of conversation between conversation with the great Khan and Marco Polo. And Marco Polo says, on the map of your empire, there must be room both for the big stone fedora and the little fedoras on the glass globe. Not because they are all equally real, but because they are all only assumptions. And so it goes. And this property suggests a new way to look at the urban landscape. When we observing and perceiving a city, we actually see a city that doesn't exist and might never exist. And this is the way we behave in a city, and plans and designs are part of this not yet existing environment. And this raises an interesting question. How to theorize about a system, a structure, whose elements, the urban agent, take decisions on non-existing entity? How to describe it? And what I suggest here, and this is is by means of information theory. And let me say a few words about information theory and the city. I will talk first about the starting point, which is Shannon theory of information. Then I will add our addition, which has to do with semantic information. And finally, the notion of information adaptation and the city. So what is Shannon information? What is semantic information? How and why do they interplay in the process of information adaptation? Now, Shannon theory, that was invented, so to say, was developed by him at the end of the 40s in a little paper, a theory about communication theory. what Shannon did in this theory, which became actually, as they call it, a seminal paper, a very influential one, what Shannon did, he looked at it from a technical engineering point of view, and he managed to develop a measure of information. When he speaks about information, his basic question is how much information can go through a certain channel. And a channel might be a telephone, a computer, but also other entities, as we will immediately see. And he showed that we can measure the quantity of information by a measure that since then became very famous. This is information bit. Okay? So we can say that this computer has so much power. What do we mean by power? We mean this channel can process so much information. Is it good information, meaningful information, rubbish? It doesn't matter. As you can see from one of his first statements, he writes, sometimes the messages have meaning. But these semantic aspects of information, he said, are irrelevant to the engineering problem. He knew, of course, that messages have meaning. But he said, I'm focusing on the quantity. How much quantity? How much information goes through a channel, through the system? And this is one of the, you see, if this was a PowerPoint, these dice would roll all the time. So you can imagine it moving. But as a PDF, it doesn't. Anyway, so this is one way to measure it. So we can say if you throw a dice, there are 6 possibilities, and you can add it to the, okay, so it would be a log of z of 6, and you can get an answer how much information, Shannon information, is conveyed by rolling a dice. Okay, now, as you can see from this simple definition, there is no need to add meaning to it. We can measure without meaning. The second property has to do with looking in the future. When we measure Shannon information, we do not measure what exists in it right now, but what might be in the future when we are rolling a dice. Okay? So it has this future-looking aspect in it. And as we will see immediately, several people in the domain of cognition already mentioned it in the past. This is the more elaborated definition. It allows us to calculate actually how much information in almost everything. In language, for example, there is a very well-known another classic paper by Shannon that measured the amount of information that exists within the English language. And you can compare, by the way, languages in this respect. Now, in this respect, or actually, it's hard to, the way they say it, it's hard to exaggerate the importance. It provided, and still providing, the basis for many theories that we are using today. All the theories that has to do with the processing of information are in one way or the other related to Shannon information theory, and this includes computer technology, communication, information sciences, and also cognitive sciences. So let me say a few words about application to cognition. One famous application came immediately after Shannon, 7 years later, a paper by Miller, the magic number 7 plus minus 2, and it shows that there is a limit to our ability to process information in short-term memory. You know, we have two kinds of memory. One is short-term, one is long-term. all the information that we face starts in the short-term memory, and only very little goes to the long-term storage of information. So there is a problem. You can see it very easily. If you start, you get someone calls you and gives you a telephone number. If it's 3-digit, you can easily remember it. If it's 5, it becomes difficult. If it's 7, 8, 9, a problem. But our brain or mind know how to overcome this difficulty by making chunks. For example, we quite often, when we have a long number, we make grouping. So we say 231 and so on and so forth, and suddenly instead of 8-digit, you have 3 digits once again. Anyway, so this is one application. Another one is in the domain of Gestalt. Gestalt theory, and here, what is nice, or what is important from our point of view, is that forms, and even abstract forms, convey information. Even abstract form convey information. For example, if you compare a circle to an L shape, you can see, if you think about rotation, that you can rotate the circle as much as you want. It will always be a circle. If you rotate the L shape, it will become all kinds of things. And specifically, if you think about it in several languages. So here, there is zero information, okay? Because there is only one possibility. Here, there are several possibilities. So actually, you have a lot of information. So information is also, it also refers to possibility. How many possibilities I have in a situation? Okay, so we can measure abstract form. Now, on the basis of this, I think it was 2003, Herman Haken and myself, we published a paper which is called The Face of the City, Its Information, and there we show that we can apply Shannon information theory to the urban landscape, what we call the face of the city. And the basic idea here, that different elements in the city convey different quantities of information. This is one element, and those quantities of information can be measured by means of Shannon information bits. Just a few examples. If you have a city where all buildings are identical to each other, it's like the circle, the information is 0. If you have a city with, where each building is different from the other, you have a lot of information, but here you are facing Miller's restriction that we find it hard to process information in short-term memory. So we have a lot of information, but this is a problem, and this is why we like very much landmarks. If you know Kevin Lynch's book about landmarks, etc., it becomes relevant. This is how landmarks enable us to find our way in the city, and we can elaborate on it in various ways. What happens when the landmarks are at certain distances? What happens when they are grouped together? They lose their power, and so on and so forth. The same can be said about the road system of cities. Now, what I want to add the following. This is one of the surprising, actually, outcomes that came from this study with Herman Haken about the face of the city. And this is the fact that Shannon information actually refers to a closed system, this specific formula. And what we show in this study, that in the case of cities, not only, but I emphasize the case of cities, in the case of cities, semantic information, that is information with meaning, enters in disguise into the definition of Shannon information. And this has two aspects. If you look at the mathematical side, you have to define the index k. The index k means that we say that those buildings form one group. Those buildings form a second group. And it means categorization. And categorization by definition, is a process of giving meaning. We take certain entities and we say they share a common quality, okay? A common denominator. And so what we suggest in this paper, that information enters in disguise into the definition of the quantity of information. And there are many other examples for this that I will skip. So what we were able to show in this paper about the face of the city was that semantic information enters in disguise. What about the other direction? Has Shannon information some effect on semantic information? And in a more recent study, this book that is called Information Adaptation, the answer is positive. We say that on the one hand, semantic information is needed in order to determine Shannon information, in order to start counting. But also, Shannon information is needed in order, how to say, to trigger, to start semantic information. And our basic empirical example here is the very process of vision. As we know from recent studies, actually not recent, but a whole set of studies that started with Nobel winners Hubel and Wiesel in the 50s and 60s, they show that information from the world comes through the eyes. It goes to a certain place in the brain. At the beginning, what our brain does, it takes what comes from the environment and subdivides it into what we call very simple entities, like straight lines, corners, and so on and so forth. So the first step is a bottom-up process of subdivisions that create local, we call it local information. Then this local information, if it crosses a certain amount, triggers a top-down process by which what we already know, what we already have in long-term memory goes down in a top-down process and makes sense out of the primitives, out of the pieces. It's like a puzzle, okay? The first step, what the brain does, it creates many pieces of a puzzle. The second step, it made a whole picture out of them. So this is in a more schematic form. Data from the world is transformed into local Shannon information, if you wish, syntactic information. This syntactic information triggers a top-down process which makes sense, and then we see something. And this is really amazing, and we call it information adaptation. And we call it information adaptation because in certain situations, the local data, the pieces of the puzzle, are not sufficient to make a whole picture. In this case, what the brain does, it adds more data that actually doesn't exist in reality. If you don't believe, look at this Canisa triangle. Okay? We all see the lines here. There are no lines in the picture, but we still see them. Okay? And vice versa in the Olympic rings. Okay? We extract unnecessary information. And the same with the beautiful story about the gorilla that I believe you all know. When we have a specific task, our brain put aside the gorilla, so much so that we do not see it. Okay? And we are speaking here on actually the way we see things. So what we suggest is the brain adapt, make a kind of adaptation between the bottom-up information and the top-down information, and this is how we see things. Now, one simple application to the city is this one. Let us imagine that here we have a city where all buildings are similar to each other, as we saw before, zero information in terms of Shannon measure. If we subdivide the city into uptown, midtown, and downtown, as in New York City, we add information, okay? And it helps us. So here we adapt by means of, in this case, language and general agreement. If, on the other hand, we assume that all those buildings are different from each other, too much information, a lot of information, too much for our processing. So what we do the exact opposite. We categorize it into uptown, midtown, downtown, and it makes it easier to us to find our way in the city. And here you can see it in a different form. We try to reach some kind of in-between. Another example that comes from a city, and here we have a link to mental time traveling. We can say, as we have seen before, that every object in the city conveys some quantity, as we have seen before. For example, let's say that we have a building which is legally defined as a warehouse. In terms of Shannon information, it has 0 bits of information because it has only one possible land use, okay? At the same time, what we suggest is that every urban element conveys also subjective information, a subjective semantic information that refers to the specific way each person perceives this warehouse. Some people perceive this building as a warehouse. If they have something to do with the warehouse, they can use it. If not, not. But let's say that we have a poor artist desperately looking for a place to live and to work. This warehouse conveys for him different future meanings, and as a consequence, different potential uses. In his imagination, in his mental time, traveling, he can see it as an apartment, a studio, a little shop, all 3 of them. So for him, the semantically determined Shannon information is, let's say in this case, 1.5 bits of information. And all this is a consequence of chronesthesia. So, and the same, by the way, happens. So actually, if you all of you, or at least you know that this was the story of the lofts in New York, and we have, this is how they started. It took 20 years until they were illegalized by the planning authorities of New York. But remember, I was talking at the beginning at nonlinearity. And this is a nice example of nonlinearity, how the act of a single person in the city transformed the whole city. Okay? And only recently, lofts became a recognized element in the city of New York. I want to close the talk by reference to this phenomenon, by reference to this artist that has changed the face of New York without intention, actually. And what I want to say that theories of urbanism and theories of planning, as developed in the 20th centuries, were based on the assumption that there are 2 camps. There are the planners on the one hand, and there are the rest of the people on the other. The planners and the planned. And they somehow interact. Okay? In a city dominated by chronesthesia, planning behavior, design behavior, such a dichotomy doesn't hold. Professional and latent planners are first and foremost urban agents interacting in the city. And actually, what we have in mind is to suggest a new field of studies, or unified field of studies, in which planning activities and design activities are not external interventions in an otherwise complex self-organizing cities, but they are part of the game, part of the urban dynamic. Thank you.
How do you see nonlinearity and planning? Will that be, also with reference to your presentation, be a harmonious couple?
Well, the major implication of what I was talking about this morning is that planning, and I believe also design, is a basic cognitive property of humans. And I think that this applies also to the relation between planning and urban dynamics. Planning is an integral element of urban dynamics. It's not an intervention in an otherwise independent system. So in the future, I believe, there will be a room to describe urban dynamics in such a way that planning actions are part of the whole urban dynamic and not an attempt to intervene.
What would be the role of the planner in that new
The role of the planner would be the same. The role of the planner would be to do what planners try to do for a long time. I mean, but there will be a difference. I mean, you see, I think that the key is to find the appropriate boundary between individuality and collectivity. Planning have to do things that individuals will not do. Very simple thing, okay? To build the road. Individuals will not build the road by themselves. So this is where planning has responsibility. On the other hand, there should be a lot of room for individual planning acts to emerge bottom up. So actually, what I see is an urban dynamics with many actors, each one at a different scale, and all of them interacting, and the result is what is practically happening in the city. That's the way.
Thank you very much.
My pleasure.